So I promise I'll not sing, just entertain you with what's coming next. So this is the last oral presentation of this session, but immediately after, we'll have a technical presentation by AutoCube and Quantum Design, which happen to be the sponsors of the Because of Prize of this year. So if you're interested, you just stay in the room before the coffee break. That was it. I don't know what to say now. Dance, sing. So I cannot think of any extras. So maybe we say, please adhere to the time. This is 25 minutes, including questions. And please test your presentation beforehand. What else? You did. Okay, so double test your presentation beforehand.
Clécio, who is in the audience, Milorad, also in the audience, and François Peters, also in the audience. And, well, this is a brief outline of my talk. So I just mentioned some things we did with forces in mesoscopic superconductors. Also mention what has been studied in Corbino disk and dynamic vortex phases, and our theoretical formulation and our analytical results. After that, I'll draw my conclusions. Well, first of all, forces have been observed in mesoscopic systems. So this is the work of the group of Grigorieva, who have studied forces in disks, and they found, for instance, these arrangements of forces in shells. Also, forces in triangles and squares as well. They have also have done some statistics on the kinds of configuration they have found, and so on. This work also, François Peters and Milorad, I think, not in this one, I don't know. But they studied the role of pinning on these forces. So, oops, what's that? Too sensitive. Okay. Why do I? Okay. So they observed giant forces as well in the systems, and well, we have studied it. That's 2004, and when I was doing my postdoc with in a group of François Peters, we studied Ginzburg-Landau and the London approach, and both give the same results for the position of forces, at least for a small number of forces in the disk. And we also studied systems with a larger number of forces. This is the phase of the order parameter for Ginzburg-Landau in London. So you see basically the same phases. And also configurations found under the London approach were also stable under the Ginzburg-Landau approach. And we studied up to 700 forces inside the disk. Well, other systems that which I would like to mention are the systems where not an external magnetic field is applied, but an homogeneous magnetic field is applied, but where you have a ferromagnet on top of the disk. And so this work was done by Milorad and Peters and Jampolsky, and was observed, and Berdiorov also. And they studied, they put a ferromagnet on top of a disk, and their simulations shown that it's possible to have stable vortex, anti-vortex pairs in the disk. And they found the region where these vortex, anti-vortex pairs are stable. And why I'm telling you about the mesoscopic superconductors and forces on that, because we want to understand this, understand better what happens in the Corbino disk. And but before that, I would like to know how we find these configurations when you have a magnetic dipole. So let's consider magnetic dipole along the axis of the disk. So here's the z-axis. And the magnetic dipole is at a certain distance from the disk. And here you have, for instance, a vortex. So we solve these equations. So this is London equation, and you can write the vortex, the current produced by vortices, and the current produced by the external magnetic dipole. We also find the streamline function and find an equation for the streamline function for the vortices and also for the magnetic field generated by the shielding currents generated by the magnetic dipole. Well, this is the streamline function for a distribution of forces inside the disk, and also you can you may find the forces acting on each vortex in the field. So based on that, you can perform simulations. But before that, it's nice to see what is the confinement potential for the dipole. And if you have a dipole which is very far from the disk, you have a parabolic potential which is the same as an external magnetic field applied. But when the magnetic dipole gets closer to the disk, the confinement potential changes a lot. So, for instance, we find that for distance of the dipole from the disk below 0.2, the radius of the disk, we can have stable vortex and anti-vortex configurations, which are shown here. So these are vortices, these are anti-vortex vortices. There are several configurations that we can find by performing computer simulations. So why I mentioned that? Because now we want to apply a radial current. So this is the so-called Corbino disk geometry. And then in this geometry, the current density decays as 1 over r from the center of the disk. And for instance, if you imagine that you have two shells of vortices, or one shell of vortex and one shell of anti-vortices, they are driven by different forces if they are at different radial positions from the center of the disk. Well, it's known that there are at least two dynamical phases. There is a rigid body rotation, which is below some critical current. And after this critical current, the external drive may unbind the pairing of the vortices, or vortex, anti-vortex here. And so after this critical currents, the shells, they may move at different angular velocities. So this is a movie for one of the configurations we've found. So this is one vortex in the center, 6 in the inner shell, and 2 anti-vortex in the outer shell. So let's see what happens. And in the right is the angular velocity against time. So you see, the configuration rotates as a rigid body. And you can calculate this rigid body rotation exactly within the London approach. But as soon as you have a current which is just a little bit larger than the critical current, they decouple. So they start to rotate, but the force acting here is much stronger, so it goes first, and this one gets behind. So the difference here is the velocity of angular velocity of the vortex and the angular velocity of the anti-vortex shells. Well, when you increase current, what happens is that these peaks in the angular velocity, they get closer to each other. So we, in fact, we characterized this kind of intershell motion with the time elapsed between two of these peaks. And if you have a much stronger current, it approaches a trigonometric function. So that's what we observe in simulations. And these results are published in the PRP last year. Well, but first of all, this problem was experimentally tackled in 1999. Okay, so they had already observed that in YBCO. And what they did was to perform an experiment in the Corbino geometry. This is a picture of their paper. And they have measured the resistance in different points in the disk, and as a function of temperature, and also as a function of current. And from this resistance, they calculated the angular velocity. And what they found is that below some critical current, there is rigid body rotation. After this critical current, there is intershell decoupling, and the different shells move at different angular speeds. This problem was studied analytically, but in the continuum limit, which means that you have you treat forces as continuums of magnetic field, and you may calculate elasticity, forces from elasticity of the vortex lattice, and you can also find these two phases from this, and also I think the approach was used a little different here by Benedetto and Marchetti, and also in this paper they also have studied it in the continuous limit. Also, there were some simulations performed. So Miguel and Zappelli had studied simulations with a high number of voices. I don't remember exactly. It's 200, 2,000 or 5,000. I don't remember exactly. But what they found, there's a movie for this configuration, and what they found was that after you apply current, if it's high enough, this part of the configuration rotates faster, and so it produces topological defects which migrate radially. And Mishko and Peters had also studied that, and is for a smaller number of forces. And they observed that there is this rigid body rotation, but when you have several vortex shells, you may have different dynamics for different shells. So, for instance, you may have two shells decoupling, but other two still coupled, rotating together. And then they have studied radial melting, angular melting, and several other things in this system. I think in this one they had observed that the inner shell rotates and the outer, and the middle shell rotates decoupled from the inner and the outer shell. Well, the outer and inner shell, they remain coupled, but the inner shell rotates faster. And they also observed some irreversibility Is it working? Okay. Well, so what we have done. First of all, we have done simulations, and we have a lot of data from simulations. But also we want to understand what happens here. And we just consider a very simple case where you have only two shells. And what happens when you rotate two shells of vortices? So first we have considered only vortices, and vortex and anti-vortices. Well, vortex and anti-vortex may be created if you have a magnetic dipole. And vortices in a disk are already observed. So this is the our theoretical approach. So we derive the forces acting on vortices within the Leonardo approach. So these are the forces, the force produced by the external current. This is the force produced by the shielding currents of the dipole. And this is the force by the shielding currents of the external magnetic field. This is the self-force which a vortex feels directed to the edge of the disk. And this is the vortex-vortex interaction. Well, if you start from these equations, then you can for two shells, you may find this equation of motion just for the angular motion, and this equation is written here. So this variable here is nothing else as the number of vortices and two shells. First of all, let me clear something, that this equation is exact within the London approach if you consider a vortex and anti-vortex shells with same number of vortices. And you neglect the image interaction. So this is equation for the angular motion. So we just treated this equation here, phi, as the angular separation between the vortex, inner vortex and outer vortex shells. And this is the equation of motion. So this is an equation which is first order equation but nonlinear. And this k is given by the distance, the radial distance of each shell. Also, we consider that the shells are stiff. So we are not, we do not consider, for instance, small deviations from the radial and position. So it's like two polygons which rotate with respect to one another. Well, but you can solve this equation. That's the good thing. And it gives you, for equal number of vortex in different shells, this critical current, which is a power law with a number of vortices in one shell, and with a ratio of the inner and outer shell. And also you have a stationary value. What is the stationary value? Is, for instance, if you have an unstable configuration without applying current, this if it's an anti-vortex and it is a vortex, they will try to be aligned. As long as you apply a current, these inner vortices are there is a stronger force acting on the inner vortices, so they start to have an angular separation. And when this angular separation cannot be sustained anymore, they start to slip one shell on top of the other. So this is here. This is the angular separation when you have a current which is below the critical current. And if you consider, for instance, that your configuration has a distance, angular separation phi naught at t equals 0, this is the solution of this equation. So I tilde here is I over the critical current. This function here is just the hyperbolic tangent, or tangent if you are over the critical current. And you also find the time between those peaks, which goes as square root of the difference of the squares of the applied current and the critical current. Well, this is a plot of the stationary solution. What I mean is when you have current below the critical current. So imagine that you have a configuration is rotating, but with some separation, and you just change the current. So the one vortex tries to move from the other, and this is how they change the position in time. And if you are with a current above the critical current, just 0.1 over the critical current, 1% over the critical current, the position, the angular separation between vortex, the two shells, they change like this, which means that they slip over one another very fast, but after that they almost move together. And this behavior changes when you increase current, and the limit of infinite current, you have linear motion, which would be the case if you don't have any interaction between the different shells. If you just observe the position of the vortex or the anti-vortex shell, this is the position of the vortex shell when you increase current, so it changes like that, and this is the position of the anti-vortex shell. What it means is that the anti-vortex is dragged with the vortex for small currents over the critical current. It's dragged along the vortex shell, and when you increase current, they start to rotate in their preferred direction, which is opposite to the vortices. Well, this is the angular velocity given by that equation. When you increase the current here, you see that the peaks are very sharp, but they start to get broader, and so you have a trigonometric function when the current increases. Well, if we perform simulations are given here by the dots, and if you have same number of vortices and anti-vortices, the calculated critical current gives you perfectly the critical current obtained from simulations. Well, the problem is that model is exact in the London approach if you have same number of vortices and anti-vortices. But the problem is, in the simulations, we also observe that frequency of that peaks with this square root law. So this is 3 vortices, 9 vortices, 4 vortices, 10 vortices, different shells. All of them fall in the same square root. And in fact, we have modeled this system just by some ansatz, and those equations can also describe these systems with different number of vortices and different shells. So this is for same number of vortices and anti-vortices, so it's square root. Also, with different number of vortices, I think this is for all configurations that we study numerically. And this is the angular separation between two shells up below the current, the critical current. So it follows what we have found, which is the inverse sign. And if you have different number of vortices and different shells, you also have a reasonable accordance. Even for only vortices, we see also a good agreement. And this in this plot here is just we fix the inner vortex positions, and we plot the outer vortex positions for different currents. So you see, if you have when current changes, the outer vortex also changes positions. and they follow uh, this dependence on the applied current. Well, and we can even do better. We can compare the analytical results with simulation, and we could find quite a good agreement. I should mention that we could not find the critical current exactly if you have different number of forces in different shells. So this was taken from the simulation. But as long as you have the data from the simulation, the curves agree reasonably well. So this is for the other configuration. This is one configuration, vortex and anti-vortices. So I finish here, and these are my conclusions. Thank you very much, and sorry for my delay.